That was the definition stuff. And then really the point of this section is to remind us about the graphs. What do the graphs of these look like? Which means on your homework today, you're going to be graphing logarithmic functions and getting into some of the applications. Yes, sir. Yes, sir. So we talked about yesterday, here's the big thing. A logarithmic function and an exponential function are inverses of each other. And there's certain things that we should know about inverses. One of them is they're symmetric about the line y equals x. And so what we're going to start with is we're going to graph both the exponential and a log. It kind of switched over now. It's much warmer now. It kind of fluctuates. Sometimes it's like super cold air blowing out, and then it changes to super hot air blowing out. Is that what it's supposed to do? Oh my gosh, that was fantastic because it's freezing. And then it got cold, so then it turned back on, and now it's warm. Crazy. Right. Yeah. I'm good. Thanks. So we're going to graph these. These are inverses of each other because this is exponential and this is log base 2. That means they undo each other. We're going to look at the graph of both of these. We graphed 2 to the x, I think, in section 3.1 like 3 times. We should be able to graph 2 to the x. But then we're going to compare that to the graph of log base 2 of x, see what happens. So hopefully we're all about ready to do this now, right? Nope. 4 2 to the x. This is an exponential model, which means as I pick bigger and bigger numbers for x, I should get bigger and bigger numbers for y. If I plug 0 in there, what do I get? Because 2 to the 0 is 1. Right? Remember that was our y-intercept, section 3.1. If I plug 1 in there, I get 2 to the 1, which is 2. If I plug 2 in there, I get 2 to the 2, which is 4, and it's just going to keep growing. 8, and then 16, and then 32, and then 64, and 128. What happens when I plug negative numbers into an exponential problem? Do I get negative numbers for my y values? You get fractions, right? This is where this goes hand in hand with logarithms. Negative numbers in an exponent does not equal negative numbers. The negative exponent actually equals 1/2. You plug negative 2 in there, that's 1 over 2 squared, that equals 1/4. And we talked a lot about this, how no matter what you plug in for x, it's never going to be 0, it's never going to be negative, so you have that horizontal asymptote every time. So when I graph this, I get a lovely little graph. Over here I get 1/2 and then 1/4. And that is what we call an exponential growth model. Yes? It's not brand new. If we graph a logarithmic graph, you have to be a little more careful in the values that you pick for your x. Like, let's start with 0. If I pick 0 in this, I get log base 2 of 0. Using our definition, what is that saying? 2 to the what equals 0? What number makes that true? Nothing, not even I. There is no number that you can ever pick that makes that true, which means, unlike an exponential problem, we're going to be restricted on what we can pick for x. Exponential, you can pick whatever you want. What happens if I pick 1? Can I do that? I would get log base 2 of 1. And again, after doing yesterday's homework, the idea of the reason I split this up in 2 days is you should be pretty good with this definition by now, and you should be able to tell me this is saying 2 to the what equals 1, right? What exponent is going to give me 1, and what's always going to be true there? 0, which means 1 is a great number to pick when you're graphing a logarithm. What about 2? Can I pick 2? When I see log base 2 of 2, 1, I gave you a property yesterday about base a of a. But again, you should be thinking this is saying 2 to the what power gives me 2. And what's the answer? 1. Now here's where you got to think a little bit more. What's the next number I can pick that I actually can get an answer for? 4. You cannot pick 3 because 2 to the what power equals 3? I don't know. Some decimal. So when you're picking your numbers, you've got to pick powers of your base. Like your base number tells you what to pick. So I could pick 4, and what power of 2 is going to give me 4? 2. Here's something else to notice. Look at the points over here on my red chart and my blue chart. What do you notice except for that first one? They're switched. Definition of inverses is that the domain and range switch places, so it should make sense to you that our domain and range are switching when we do this. Which means, what happens if I pick 1/2 for my x value? Yeah, because I'm saying 2 to the what power equals 1/2? It's -1. And if I pick 1/4, I'm going to get -2. So when I graph this, instead of having a y-intercept of 1, I have an x-intercept of 1. 2, 1, 4, 2. What would be the next perfect square if your graph might not go this far? 8, 3. And it's really important that you pick these fractions or that you're aware of what's happening. Because if you just make this graph, that looks like a square root graph to me, and that's not going to get you your points. You got to know that this actually keeps going. It's just never actually going to get to 0. If I pick 1/2, I get -1. If I pick 1/4, I'd get -2, and then I'd get -3 for 1/8. And just like before, I'm going to have an asymptote. But what's different about this one? Yeah, it's a vertical asymptote. It's along the y-axis instead of a horizontal asymptote. Again, that's because the domain and the range switch places. You will always have a vertical asymptote on this. What's my domain of this problem? Tyler? 0 to infinity. That was my range of my exponential graph. Right? My domain and range have switched. Your domain will always be restricted on a log graph because you can't take the log of 0, you can't take the log of a negative number. What's my vertical asymptote on this? Sean? X equals 0. Remember, with vertical asymptotes and domain, they're the same number. So if you know one of them, you know the other one. Your book is going to focus a lot on ln. I'm not a big fan of graphing ln because that means I'm going to be graphing decimals, but we can do it. It's the same thing. So let's look at that. The domain range? But do you really want to make it 2 xy charts every time? Could, I guess. But you could. But yes, they were. If you have the inverse, so whatever logarithm they give you, if you graphed its inverse exponential, they would always be switched. But I don't think that's the best method to graph every time. Because what if they throw in something really weird, like log 5 chance, what would be your, I would know. No, this is better. Like, it's not 2xy charts. I don't want to graph 2 every time. If they only ask me to graph ln, I don't want to make the inverse. What would be the inverse of ln of x? E to the x. So technically speaking, if you wanted to make an xy chart for e to the x, switch them around, it would work. But we're not going to. We're going to practice this way. Find the domain, the x-intercept, and vertical asymptote, and we're also graphing this. The domain is going to be hopefully something you can do. The domain is you can't have the ln or log of 0 or a negative number. So looking at this, do you agree that I'm not going to be able to plug 0 in this one either, just like the last one? Doesn't matter that I've changed ln, it's still ln of x. Log base anything of x, my domain is going to be 0 to infinity. Unless there's a transformation, which we'll do in just a second. That's going to be your domain. Unless you shift that over one way or the other. But I'm just going to make an xy chart. This is where you need a calculator, because I don't know powers of p off the top of my head. And I don't expect you to know them either. But I can do one. I can't pick 0. What if I pick 1? Can I do that one without a calculator? Yeah, ln of 1, or log of anything of 1, is always going to be 0. Unless there's a transformation. But other than that, we're just going to use our calculator and get some numbers here. So if I plug 2 in there, that's like saying e to the what power equals 2. And it's not so pretty. I think I get like 0.693. What else do you want to pick? 3. If I pick 3, I'm just going to type in ln of 3 on my calculator, and I get 1.099. That's not very exciting either. I always think it's a good idea to pick a fraction, because remember, fractions are going to give you that negative exponent. Sean says 1/2. I'm fine with that. If I type in ln of 1/2, I should get a negative number there, and I do. I get negative 0.693. And you can pick whatever you want here, but here's the great thing. Just like exponential graphs are always going to look a certain way, like where they have that horizontal asymptote and either go up or go down, logarithmic graphs are always going to look a certain way. So if you just pick a few points and you know where your asymptote's going to be, you don't need to pick a million points here. These are really small numbers, so I'm going to make my graph a little bit go by half here, so I don't have such a squished little graph here. One zero to negative 0.693, so that's just a little bit above a half. And at 3, it's barely over 1, which means, do you agree this is kind of going up very, very slowly? Logarithmic graphs do that. At 1/2, it's negative 0.693. And since my domain is never getting to 0, what's my asymptote also going to be? X equals 0. It's the same thing, whatever that number is. If your domain can't be 0, your asymptote is x equals 0. Which means when I graph this, I know that this side's going up very slow, and this side I need to show that I'm aware that that's an asymptote and that it's getting closer and closer to that y-axis without ever reaching it. What's the x-intercept of this? 1. Again, that's going to always be true unless, again, it's shifted. These are kind of your base things. I call these the parent graphs. And then if you know your transformations and you're going to move stuff around, it's going to shift things around just like with our exponential. So let's look at one that has a transformation, and I think that's it. How do you feel about this? Hungry, that's not a feeling. y equals negative log of x minus 3. Again, your book likes ln and it likes common logs. Those are the ones that are used the most in applications. That's why your book picks those the most. I like other ones because it makes you do it without a calculator. Looking at this one, before I'm even starting, I'm going to think about my transformations. What does subtracting 3 on the inside of the function do to my graph? It moves it to the right 3, which means that whole graph is going to shift to the right, which means my domain and my asymptote are also going to shift to the right. That's something really important to notice. Also, what does this negative out front mean? Yeah, it reflects over the x-axis, which means instead of going like this, it's going to flip up, and the asymptote's going to be going up. And so you don't have to use the transformations, but to me the transformations are very comforting. When I know what it should look like, I can make sure my points match it. Can you tell me what my domain and or my asymptote is going to be on this one? What is going to be the number that I can't ever plug in, or any number smaller than that? This can never equal 0. So just like with a fraction, you know how we find our domain? We said the denominator equal to 0 and we solve it from there. It's going to be the same thing for these. This is not allowed to equal 0. So if you're trying to find your domain, you're going to always set that is not allowed to equal 0. So when you solve it, that's not right. It's not allowed to equal 3, right? You follow me on that? But is that my domain? Is my domain only I can't pick 3? What else can I pick? So can I pick negative, can I pick 2? Can I pick 1?
Greater than 3.
Right. Well, it's kind of the question I'm asking here. We're not allowed to pick any number less than 3. Do you agree with that? If 3 is what makes it go to 0, anything less than 3 is excluded, which means our domain is greater than 3. So I would say either my domain is x is greater than 3 or from 3 to infinity. So it's not just that you're excluding that one number, okay? I think it's a good idea to start with that because it tells you where to start your XY chart. Don't pick 0, don't pick 1, don't pick 2, don't pick 3. Can't pick those. So what's a good number to start with? 4. And this one is log base 10, but I want to show you how we can really do this without a calculator. Because if I plug 4 in there, what do I get inside there? 1. And what's log of 1? And even though there's a negative in front, negative of 0 is still just 0. Good place to start. Notice that normally my x-intercept is 1. I've moved it over 3, so it makes sense it's at 4. We'll pick some numbers with our calculator in a minute, but let's say this was not base 10, or let's pretend our calculator doesn't do base 10. What would be the next number I could pick for x that would give me a power of 10 inside this little parenthesis here? Sean says 13. What happens if I plug 13 in there? You get 13 minus 3, which is 10. Just like that first one, we were picking powers of 2. You want to pick things that give you nice numbers if you didn't have a calculator, which obviously you do. You don't have to do this. But I just wanted to show you that. And what would log of 10 be? Right, remember this is 10 of 10, so that's 1, but it's negative, so it's negative 1. Maybe pick a couple more numbers using your calculator. So what if we picked, I don't know, some number not as big as 13, like 7. And normally we pick a fraction, like the last one Sean picked 1/2. What would be the number I could pick, like getting closer to my asymptote? It has to be something that's going to give me a fraction in here, smaller than 1. It couldn't be 2, because 2 minus 1 is negative 1. Couldn't be 3, because 3 minus 3 is 0. And we already picked 4, so you got to pick something between 3 and 4. And Sean said 3.5, and I think I agree with that, too. So plug those in your calculator and make sure we agree on our numbers. Hi, Judy.
Hello, Miss Jason.
They were talking about me, not you. I've had a rough day today. I don't know. I'm just grumpy. No, I'm just grumpy. Well, I do know why, but I don't really want to say. Miss Dixon's room. Yeah. Yeah, can I send a ride at before the bell rings? Okay, thank you. Bye. Georgie, you're supposed to go to the office, but you're not allowed to go yet. So if I graph this, at 4, I get 0. At 13, I get negative 1. At 7, I get negative 0.602. And at 3.5, I get a very small number like 0.3. Where's my asymptote going to be? At 3. Here's my advice to you. It's really easy to connect this and not pay attention to where your asymptote is. I'm going to draw in my asymptote as a dotted line to remind myself, don't let my graph go past there. So I'm going to make this side go up and this side go down. I feel confident in that graph because it's flipped over. That's what the negative tells me. And it moved right 3. You follow me on that? Your intercept is 4, yes. Here's kind of a summary of our domain and range on these. If it's just log of x, ln of x, your domain every time will be 0 to infinity because you cannot take the log of 0 or the log of a negative number. What about your range on all these? I didn't do it, but what's the range going to be? Yeah, all real numbers. And if you go back and you look at your notes from 3.1, you'll see that that exactly switched from the notes that we wrote out for exponential graphs. Exponential graphs, the domain is all real numbers, and the range is 0 to infinity. They'll always have an x-intercept of 1, 0. And they'll always be increasing and continuous if there's no transformation. This is all in your book in a little chart. I don't know that the increasing continuous is that important, but this part really is important as you're doing these. There are 3 of these that you're graphing on your homework tonight. I believe they're ln and log base 10, which means you can use your calculator. But think about them of maybe what I could pick if I didn't have a calculator as well. There's also some on your homework that are story problems, and I'm sure we'll talk about at least one of them tomorrow. One of them says, go back and look at example blah, blah, blah to use this formula. I expect you to go back and look at that example. It's just a formula, and you're just plugging it in. Look in your book. That's why you paid the money for it. This is 3.3 day 2.
I'm going to take
37 through 40 are matching. They give you 4 graphs and 4 equations. Use the transformations to help you match those up, okay? But you have 3 graphs that you should be graphing. Okay, Georgia, you can go.
what time do we get back?
33. I don't know the graph papers would be very beneficial on these because they're very terrible numbers.
We have like a minute.
How do you get like 3 minutes? It's only 1:30. Remember that your test corrections are due Monday. I'm still missing.
Okay, can I still have one more?
I'm still missing a lot of people's test corrections. Remember, that's a grade, and only one person has retaken that test. You have today, no, it's over,